here for Friday during part-time in Mr. James' room. Remember again, students, they'll resend the email. If you're planning on coming to prom, you get a ticket. We'll start selling those, I believe, tomorrow. Seniors get a free ticket. Some juniors do. But we purchase a ticket. They are $25. If you're an out-of-school guest, a freshman or sophomore to prom, grand march, or the dance next week, or both proms, you sign them up. Those forms are due.
4, 1 2 4, 1 2 4, 1 2 4, 2 3.
Remember, post prom is not a school-sponsored event. They control that. If you're a junior and you want to help decorate for prom, stop in and visit Mrs. Waters. Your parents must excuse you, and that must be done by 3:15 next Thursday. If you're not excused by that one time, you won't be decorated. It is also the day we are hosting and participating in the Spirit Push Invitational Track. Native American seniors, make sure to check out the news on the opportunity to do the senior honoring and feathering ceremony and rapid speaker sheet. Stop in the guidance office, Mrs. Murphy or Mrs. Harmon, if you have any questions on that. And today is the day. Seniors, if you're interested in Build Dakota Scholarship, your app has to be in, or you are late. All please stand to the pledge. To the flag. All have a great day.
Should be fairly quick. Who's still going? Couple? Okay. Okay, looks like most of us are there. I know. Can't even see it. There. We'll do like this. That's better. If I know that that's a right angle, then right triangle trig is live. I get to do Pythagorean Theorem to find my missing guy. It's going to be square root of 8 squared minus 6 squared. 64 minus 36. What's that? 28? 2 root of 7? Okay. And then go find your other two. Remember how we said we're going to do this? Where if you find one, it's okay to find the other one by just subtracting from 90. Or add 90, I'll subtract from 180. So you have to have one of these two. Measure of angle B is going to be the arc cosine, adjacent hypotenuse, of either 6 over 8 or 3 over 4 reduced. Both will work. So this one would have been arc sine of 6 over 8 or 3 over 4 reduced. So I'll just kind of put the whole gamut up here. So you have to have one of those two, and then your decimal equivalents can subtract from 90 to find the other one. So, because this is in slideshow mode, someone with the magic buttons who is in degrees, what you got?
Well, I got for angle B, I got 41.4.
Confirm. Bobbles across the room, which means this guy's got to be
48.590.
okay. So again, you have one of those green things, but both of the yellow things. Now, if you did the arc function to find both angles, great. The secant of A. Well, from angle A, secant, opposite of cosine, also right up here, is hypotenuse over adjacent. So 8 over 2 root of 7. Make sure you reduce, make sure you rationalize, and make sure you don't drop things that are expensive. You get 4 root of 7 over 7.
About 40.516? Or did you not?
I want that. Okay. That is the actual secant. Yeah. So we should have one of these by Pythagorean. Both of our approximations and our simplified secant. Okay. Now, who got caught in the trap and was in radians? Because someone always does it. Really? Sweet. Okay. Good. Come on now. There we go. Yeah, we got to get a little funky up here because for some reason Google Drive isn't syncing at all. So I'm having to, like, the video is going to look weird. Some of the picture files for just like side scroller gone and all that, but we can still get business done. Homie work.
With the secants on the last problem, would we have to write like, I guess, like anything in front of our answer, or would our answer just be like the 7 over 4? So would we write the cos?
Oh, it'd just be the secant A is, but since it was specifically asking for secant of A, if you just wrote 4 root of 7 over 7, good. Yeah. And there. Okay. Without a calculator. Okay, it's going to be super pixelated, but we can fix that. Is it 4x? Yeah, it's 4x. Five root of 3? Okay. Again, if you don't know your special right triangles, your 30-60-90 and 45-45-90 ratios, if you didn't have a ton of experience with them in geometry, I'm going to have a another little cheater here for you, where this is 1, 1 square root of 2. The legs are the same, right? So next to this, I would always have my geometry kids write that if I'm going from leg to hypotenuse, I multiply by square root of 2. If I'm going from hypotenuse to leg, I divide by the square root of 2. If I'm on a 30, 60, 90, which is square root of 3, 2, 1, you have the short leg, the long leg, and the hypotenuse. You just write on there, how do I get from this to this to this? So how do I go from the short leg to the long leg? Multiply by square root of 3. So that means to go from the short leg to the hypotenuse, I multiply by 2. To go from the long leg to the short leg, I divide by square root of 3. To go from the hypotenuse to the short leg, we're all kind of switching back and forth right here right now because if something's a ratio of 1, it's going to be the easiest to work with. I'm going to divide by 2. I would always have kids write that. So when you run across a problem like this, how do I go from long leg to short leg? Short leg to hypotenuse. 8x minus 10 is 5x minus 4. That's it. And then solve. Subtract 5, add 10, get 3x equals 6, x equals 2, plug them both back in, you're good to go. Now another way to do this, and I didn't even look at what the solutions in the book were, is if they're trig ratios, then literally use ratios. You can say that the 4x square root of 3 minus 5 root of 3 is in the square root of 3 spot. So that should be proportional to the 5x minus 4 is in the 2 spot. Or you could say the whole means extremes thing in there. This is the 2 spot, that's the square root of 3 spot. This is the 2 spot. This is the square root of 3 spot. Okay? Which is just swapping the means and extremes again. So it's a ratio. This is in this spot, that is in that spot. Kind of like those old, remember, like physical science, geometry problems where it's measure the person's shadow, measure the tree's shadow, measure the person's height, how tall is the tree? You compare similar things. This is a 30, 60, 90 triangle. So it is similar to all other 30, 60, 90 triangles. I can set up a proportion. In which case, here I would just womp. 4x minus 5 times 2, 5x minus 4. Here, if you do the multiply and divide business, it's a little more tiresome, but you will have this side by 2, this times square root of 3. Well, now every single term is times square root of 3, so you divide everything by square root of 3 and they go away. Okay, so a bunch of different ways to do it because that's how proportions work. Literally, that was one of the papers I did for undergrad years ago was, or a whole research project was proportional reasoning. Some people can just look at it and say, well, just times that by 2. Okay, then multiply it by 2. Okay. So whichever way you do it, whether you're using these shortcuts to set equal, or you're setting up proportions, both are going to work. Ooh, fourth option. From here, I have adjacent and hypotenuse. So I could say the cosine of 30 is 4x squared root of 3 minus 5 root of 3 over 5x minus 4. But then I know that the cosine of 30 is and then cut out the middleman. So, different ways to do it. Utters. No, okay. Womp. Okay, so we talked about the stuff. We got through the DMS thing. That was just one of those side quests that we need to do for one or two of the application problems. So, back to this. we said that that special circle is just a bunch of our special right triangles, right? They're all counting by 30s and 45s. Which means I can chop it up into quarters, and then eighths, and then sixths and twelfths, and it's just a bunch of fractions. That's what leads into the definition of a radian. Okay. String. I have no string. We got better than a string, though. Okay. It's a really good fidget. The jingles. We like the jingles. Okay. Imagine you have, this is tethered, right? What happens when I try to come up? It's locked in place, right? So if this is a definite length, it also is going to define an amount of rotation. If this is a specific length, it matches a specific length or a specific amount of rotation. What if I just made that length the radius? Radius, radian. What someone figured out is, instead of measuring degrees, instead of measuring portions of 360, what if I just said everything is based on the radius, so I only need to know one measurement instead of two? And that's exactly what they did. They took this measurement here to here, and they said, I'll take this much distance, whatever the radius is, and I'll go that far. And then, thunk, it's done. And I will call that amount of rotation a radian. And now it's a whole new measurement of rotation. Just like you can measure in Celsius or Fahrenheit. You can measure in kilometers or miles. This is just a different way to measure them. And the majority of what you will do in trig is based off of radians instead, because then it's all like a self-contained, self-referential system. If that is 1 radian, that's your big thing. 1 radius, which is in length, is 1 radian, which is rotation. This is a big King Kong holy crap thing, because I get to use this to swap back and forth between linear distance and rotational distance. For example, who's ever just stomped on the gas getting around Granny, and you see your RPMs, 5,500, 6,000. You just took like 6 years off the car's lifespan, but hey, you got around Granny. What gauges like that in a vehicle or any other instrument will do is they're going to take the radius of something like, oh, I don't know, a crankshaft. And they'll say, well, if it rotates this much, that means it's covering this much linear distance. And if I can have that much linear distance, I can do unit analysis. Remember back in physical science? Meters is to meters, kilometers is to kilometers, hours is to hours. Crossing those out, it's a unit conversion from it rotates this much to I physically move this much linear distance. That's why if you ever put different sized tires on your vehicle, your speedometer is no longer accurate. You have to adjust it. Okay? I just got new tires on my truck. They're just a hair, like a ½ inch wider. My speedometer is no longer accurate. I had to get that adjusted, and I had to specifically request that they fix that in the computer when they put on a new set of tires. Because otherwise, I'm going to think I'm going a speed, and I ain't. It's going to say that I'm going 70, and I think that's the 5-mile cushion, and turns out I'm going 72. Whoop, whoop. There he is, right behind me. This is huge, and we are going to use it in unit analysis. We're going to use it in conversion problems. We're going to use it in application problems. 1 radian is 1 radius. So if this length of distance is 1 radian, do you remember what's right over here? If this is 0, how many degrees right there? What do you think is going to happen here? 1 radian, 2 radians, 3 radians, and change. What do you think that change is? 1415926 ... Pi radians is 180 degrees. And that is our conversion factor to switch back and forth between radians and degrees. So I want you to think back to some of the problems that you did on here when you didn't have it in radians. Or sorry, you didn't have it in degrees. Say my mode was over in radians. I go to do a thing on calculator. Maybe, for example, I did the arc sine of 6 over 8. And I get something that's wrong. I just got an answer in radians. So if 180 degrees is pi radians, what do I do to go from radians to degrees? Multiply by pi and then divide by the 180. If I take this, or sorry, the other way around, I'm thinking from degrees to radians. Multiply by 180, divide by pi. If I take this times 180 and divide it by pi, and that was what we had for our angle measure. Okay, so it's a straight conversion between the two. And that allows me to take this circle and start chopping it up in terms of radians instead of degrees. Okay, we just said that a half a rotation is 180 degrees. And 180 degrees was pi radians. So what's a full rotation? 360, which is 2 pi. Okay. Now, probably the last time you saw that was, remember, circumference? Circumference is 2 pi r, 2 pi radius, because it's 2 pi radians, all the way around. Okay, and now if this is 1 pi, the rest of this just becomes, can you do fractions? Can you cut the pizza up? Okay, well if this was pi radians, a quarter rotation, we know that's 90 degrees. Well, if that's pi, pi over 2. And we are going to write it as pi over 2 instead of 1/2 pi, like a coefficient. And you'll see why as we move through the next few sections. 1/6 of a rotation. Again, this is pi. 1/6 of a rotation, well, what's 1/6 of 360 degrees? 60 degrees. And I'm 1/3 of the way to pi. So, pi over 3. And it's right down there at the bottom. The conversion between these is oh so simple. If I'm going to go from degrees to radians, it didn't have pi in it, now it needs pi in it. Think about that. Degrees times something, and now it's going to have a pi radians. If you remember your old unit analysis, shouldn't I have degrees down here and then radians here so that they can cancel? And we said that pi radians is 180 degrees. Just like we did with unit analysis back in physical science, when you would start crossing out 1 hour and 3,600 seconds. Cross, cross. Okay? So I'm going to multiply by pi over 180 to go 2 radians. If I'm going the other way, saying radians go to degrees, well, I want the pi to disappear. So it needs to be on a denominator. I want degrees to show up, so degrees needs to be on a numerator. I'm going to multiply by 180 degrees over pi. Okay? It's a straight conversion factor. If you need to make a note to yourself as you're doing these, if you're converting back and forth, usually at the beginning of chapter 4, kids would rather work in degrees and then convert to radians. Even if the original problem was in radians, they'll switch it over to degrees, work in degrees, and then switch it back to radians because we don't like fractions. Use the pi button. Don't you dare use 3.14. Don't you dare use 22/7. Use pi button. Okay? How many of you even knew the 22/7 thing? Try 22 divided by 7, see how close it is. Okay? So 22/7 would be used as an approximation because it has 3.14 and then stuff to take place of stuff. So it's not cut off at 314. So each of these, it's nice and simple. Turn degrees into radians and radians into degrees. If it's 120 degrees, I multiply by pi over 180. My degrees cancel out, turning into radians. And get, well, maybe we should reduce this down too. 180 and 120, well, if I divide by 10, and then I divide by 6, I get 2 pi over 3. A negative 45. That's fine. You're just going to have a negative angle in radians too. Multiply by pi over 180. Degrees cancel out. 180 and 45 becomes 4 and negative 1. So negative pi over 4. If I'm going the other direction, I'm in radians, I want degrees. I have no idea what 5 pi over 6 radians is, so I'm going to take it times 180 over pi. I'm going to take it times 180 over pi. Whether they're positive or negative angles doesn't matter. 6 and 180 becomes 1 and 30. Pi's cancel. 150. Pi's cancel. 180 over 2 is 90. 3 by 90 is negative 270. Okay? No joke. Unit analysis. You're back in physical science. Okay? How many times throughout math in the last year have you been, I miss the good old days? Okay? It kept getting more complicated. Can't I just cross numbers out and solve one variable equations again? I was good at that. So, each of them, swappy swappy. Ooh, shiny. Fairly quick, right? As long as you know how to reduce a fraction, you didn't forget that somewhere along the way as you were taught how to use a calculator. Okay, that's 5 to 5, 7, 3, 4 pi this way. So it's 210, right? No, that's 240. I'm tired. Okay. And over time, as we're working with our unit circle, you're going to become really good at knowing those. In fact, what you should know, that circle on that first page, that was all in degrees that you said you had never really seen before, you should know that in radians instead. The degrees thing is kind of helpful. The radians thing is what matters. And it's just about fractions. It's just a bunch of fractions. Okay. Coterminal angles. You hear the word in it, coterminal. Terminate at same spot. Meaning, sometimes you can have an angle where I get the positive angle. Remember, that's counterclockwise rotation. Where about would this angle be? What do you think? How many degrees?
That's between 180 and 270.
Uh-huh.
I have no idea.
Looks about halfway there, too. 225. Or, I could also say, in radians, anyone? Yeah, 225 pi over 180 and reduce it. There you go. 5 pi over 4. Got a little too excited there, bud. Okay. The negative angle that also terminates in the same place. So it has the same initial side, the same terminal side, but it went the other direction, so it's going to be negative. Those angles, well, altogether, there's 360 degrees, right? So if I go 225 this way, how far do I have to go this way to make a grand total of 360? 135. So it's just a negative. Well, if altogether my this way and this way make a full revolution, and that full revolution is 2 pi radians, how many more radians do I need to get from 5 pi over 4 to 2 pi? 3/4, 3 pi over 4. It's just they're going to be negative, okay? So these are positive and negative coterminal angles. Where they get a little goofy is when I need a positive coterminal angle with an angle that was already positive. So the original angle, alpha, about where do you think that is? Which of our special angles is that? Right? It's more than 45. The three angles that are in that quadrant are 30, 45, 60. It ain't halfway. It's more than halfway, so we have to say that this is 60 degrees, or, yes, you think how far, instead of just doing a straight conversion of 60 over 180, how far towards pi was it? It was a third of the way there. So it's pi over 3. Okay. Well, if I want an angle that's negative coterminal that's easy. I just go the other way. But I want a positive angle that's coterminal to it. If I do blue, can you all even see that? Okay, not too much, so we'll go with the regular blue. If I want the positive angle with it, well, I have to go this way because it's positive. But I can't just stop there because that was my original angle. And if I want to end in the same spot, I got to go all the way around the block and try it again. That's my positive coterminal angle. So if it was originally 60, and then I took another lap, 420 degrees, or if it was originally 1 pi over 3, and I took 2 pi more, well, 2 pi in terms of thirds is 6 pi over 3. 6 pi over 3, 1 pi over 3, add fractions together, you got 7 pi over 3. Okay, so positive and negative coterminal angles are all about together they make a full revolution. Some will be positive, some will be negative. The rule for them, can you come up with a rule of how did I get a positive coterminal angle? What can I just do if I have the angle and don't want to draw it at all? How do I say a positive coterminal angle with 60? Well, it's positive, so I'm going to add, and I add a full revolution, 360. If it's in radians, I add a full revolution, which is 2 pi. That's the rule. If I want a positive coterminal angle, add 2 pi, add 360. If I want a negative coterminal angle, I heard the mutter, subtract it. Subtract 360. Go back to that other one. You were at 225 degrees. What's 225 minus 360? Negative 135. Okay? So you're going to keep adding or subtracting 360. You're going to keep adding or subtracting 2 pi. And that are my rules down here. If alpha is the degree of any angle, the angles measuring alpha plus 360n, where n is an integer, are coterminal with it. So when they ask me, name all angles coterminal with 77 degrees. Well, 77 is alpha. So all angles coterminal with it is 77 plus 360n, where n is an element of the integers. Remember our set builder notation? Okay. Same thing happens over here, except now we're in radian mode. If I said find all angles coterminal with, I don't know, say it was like 5 pi over 3. Well, that's my alpha. I'm just going to keep adding iterations of 2 pi to it. So I'll say 5 pi over 3 plus, you can say 2n pi or 2 pi n. I really don't like that they say 2n pi. Like, I understand why they do it, because once n is an integer, say it's 3. 2 times 3 is 6. I'll add 6 pi. That makes sense. But right now, pi is a number, 2 is a number, and n is a variable, so the variable should go at the end. Right? Like, it can go in either spot. So if I say plus 2n pi where n is an element of the integers. Why do I have to keep saying n is an integer? Why do I have to add 2 integer pi to get a coterminal angle? What, can I pick a real number that's not an integer? Like a half. Can I add half of a revolution and end up at a coterminal angle? Can I add half of a revolution and still be staring in the same direction? Right? It has to be one full revolution, a whole number. Well, then why don't they just say whole numbers? Why do they say integers? Positive or negative, right? I can add a full lap. I'm going to get dizzy. Or I can add, subtract a full lap. I'm tired. Baby Bear was up from like 1 to 3 again. That poor child. Yes. It was a really bad Z.
Like a really fancy H.
Mom, they're picking on me. Okay, so if they ask for identify all angles coterminal with it, I'm just going to use that set builder notation. All angles coterminal with 45 is 45 degrees plus 360n, where n is an element of the make a good Z. That's it. Like, it's always that. You just change the number in front. Now here's the catch. Draw and label one coterminal angle, both positive and negative. I'm going to get those artiste skills back out. Okay, start with 45. Where's 45 degrees? Halfway through quadrant 1. So I'll do this and say that's 45 degrees. If I want the negative coterminal angle with it, well, off to the side here, I'm going to say 45 degree, 455 with it. There we go. Oak, there it. If I want a negative coterminal angle, I'll subtract 360. 45 minus 360 is? Negative 315. So I draw my negative angle going the other direction and say it's negative 315 degrees. If I want a positive coterminal angle, I will add 360, which is 405. And to draw that, remember, you have to go all the way around the block and try it again. Here's positive, but I can't be there because that's where my original is, so I keep going. Another lap. Okay? It's an old building vault stand-up bit. He was talking about people who rent RVs not knowing how to back them up. Like you'd pull up to the gas pump and there is no backing it up. It's go all the way around the block and try it again. So that's what you got to do. You tried to go here. Oh, wait, someone's in my spot. The original 45. Go around the block and try again. Same thing happens in radians. First up, the coterminal angles are going to be alpha, whatever the angle was, so in this case, negative pi over 3, plus 2n pi, where n is a integer. Okay. So I start at negative pi over 3, and then I'm just going to keep adding or subtracting iterations of 2 pi, because that's a full circle. Like, come on. I know that everyone in here at some point has sat in the little spinny chair, closed your eyes, and just keep going around, and then you try to stop yourself, and it turns out you're like aiming the wrong direction now. That's what you're trying to do. You're trying to aim in the same direction again. Do you know that when you go super fast in one direction, you get super dizzy? If you just reverse real quick, like 2 or 3 laps, you're fine. It rebalances the equilibrium because your inner ear has fluid in it. So when you keep spinning one way, the fluid tilts like this. And that's why it feels weird when it settles. So if you just real quick whip yourself the other way, it'll do that and then settle. And now you're fine. So if you ever have those like barrel races or whatever where you got to put your head on the bat and spin around, you do your 10 laps, pause, do 2 laps the other way, and then you can just sprint and everyone else is falling over. Because someone regularly stims by spinning in their chair. So, where is... Wait, this works? Yeah, it does. Where is negative pi over 3, though? Which quadrant? Let's just start with which quadrant. It is negative 60 degrees if you do the conversion. So it'll be down in the 4th quadrant, about 1, 2, 3, about 1/3 of the way to pi. Okay, so that's how you measure it. About 1/3 of the way to pi, I mark it here and I say that's negative pi over 3. Now, last time I wrote them off to the side. You can write them off to the side if you want, but I'm going to put them on here this time. Actually, y'all need to see fractions because we can't fraction. If I try to make a positive coterminal angle, what am I adding to it? I'm adding 2 pi, but I need common denominators. 6 pi over 3. So if I go this way, for my positive angle, I get to 5 pi over 3. Right? 5 pi over 3 and 1 pi over 3. Some is positive, some is negative. Altogether, it makes 6 pi over 3, which is a full revolution. If I want my negative coterminal angle, I subtract 2 pi, which I have to turn into 6 pi over 3, so I have common denominators. Getting negative 7 pi over 3, which, here's my negative angle, go all the way around the block and try it again. Okay. You already have a negative angle. So if I want a negative coterminal angle, I have to go past that one. Okay? You're running laps around the race. Where's my track kids? Okay? Keenan. That kid's fast. So what if he wants to pull a Lightning McQueen and just lap everyone to get his time? Well, I get over to where Caden is. I better go faster so that I can lap him and still get up at the same spot, right? If my negative angle is here and I want to end up in the same spot, you gotta go all the way around again. You gotta lap him. In a 400?
That's what Caden just did. He just got lapped in a 400. You said he came all the way.
Oh, okay. Oh, so you're the sprinters and not the distance runners. Okay. See, I like doing the hog jog in track in high school, the throwers relay, because I can sprint. I have a heart attack afterwards, but I can sprint. When I was coaching middle school football and I chased that little smart aleck down from behind, Mr. Hot Stuff, I'm just going to bounce to the outside and run around everyone. When he sees the guy trucking behind him, about keeled over afterwards, but I caught him. Go ahead. You do not stop running until you hear that whistle, kid. Okay. So remember to write all coterminal angles. It's just that set builder notation. And then, can you draw where these are? If you got to refer back to your, if you got to refer back to those circles, go ahead. I'd recommend before you go starting to draw the coterminal angles, maybe check with the neighbor to make sure you're in the same quadrant, that you drew it in the right spot. You get all these fractions and pies and loop-de-loop circles within crosshairs, and it looks really fancy. It'll make you feel smart when you show someone, but it's just drawing pictures and adding 360.
So if it's still 11 pies, we have to go around 4 times. It's more than one rotation. Like, because if 2 pies, 1 rotation, 11 pi over 4 would be like.
Well, yeah, that's how you get your positive coterminal angle. You got to go all the way around and then lap them. Yep. Okay, you got your coterminal angles. It's just that set builder notation. It's the same every time. Negative 30 should be a third of the way to your south pole. Three pi over 4, halfway through quadrant 2. So make sure you at least got that right. Again, a window into how I grade the tests. If I have a kid who puts it in the wrong spot, but they still found their coterminal angles and they're right, they're just also in the wrong spot, one off. Like, you should know where that angle is. Okay, that's the gotcha moment, Simon Says style. Everyone look straight ahead. Remember, with our inverses. Everyone turn your head 90 degrees to the right. Everyone turn your head 90 degrees to the left, and you got that kid who does this. Okay? It happens, right? Sometimes you just goof and the whole thing is screwed up, but did you do the right thing based on incorrect information? Okay? So if I want a positive coterminal angle, I'm just going to go the other direction. Negative 30 plus 360. 330 degrees. If I want the negative coterminal angle, well, this is already negative. I got to go all the way around the block to lap them. So that'll be at a negative 390. If I want my negative coterminal angle, that's nice. I just go the other direction. 2 pi minus 3 pi over 4, or 3 pi over 4 minus 2 pi, is going to be a negative 5 pi over 4. But if I want my positive angle, I have to go this way. He's in my spot. Gotta lap him. And I take 3 pi over 4 plus 2 pi for 11 pi over 4. Now, let's talk about that kid. I have a feeling it's Finn. Oh, he's in my spot. 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 36, 36. Is it a negative coterminal angle? Did I show all 10 laps? I think so. It ain't wrong. I had a kid about 4 or 5 years ago on their test. They did, what was it? They got bored. They finished early and then went back and just redid the problem with, I want to say they tried to do 100 revolutions. They tried to do 100 revolutions, but they ran out of room in the corner of the paper. So they had to cut it off at like 82 or something. Yeah. It depends if you see value in it. I've seen all of your D&D stuff written in your book. So. Got him. So, we did the DMS thing. Straight conversions from radians to degrees. Fairly simple. Are you okay with these? Yeah, a little bit hesitant. Do we need to do the radian stuff again? Okay. One more. Do it in radians. I think you'd be fine in degrees. I want you to practice it in radians. Where the honkin' heck is negative 7 pi over 4?
Do you like associate numbers with feelings, or just like that's a good number, that's a bad number? Because I do that. Like
It's Sullivan. He does not have.
Ow!
No, but like sometimes I'll just say
Quite
a
the
number and be
opposite.
like,
I'm
oh,
incredibly impulsive and emotional.
that's a good number. Like 12, it's a good number, but only when it's like made by 3 and 4 quarters. And like I also associate colors to like different multiples of numbers.
That I do. Everything is colors and shapes to
Like
me.
3 and 4 is pink and blue. Yeah. Okay. 6 and 2 is yellow and purple. That makes sense.
It sounds like when you ask the little kid what color or what kind of Kool-Aid they want. I like the red flavor.
Yes.
What flavor ice cream do you want? Green.
Okay, there's a lot. There's 3 different spots. I did not have the guts to try.
Come on, draw it. Draw it, draw it.
2 pi is just 1 You can check one.
Do you have it drawn yet?
We definitely did not get.
Mm-hmm.
This is 2 pi 180 or 360.
2 pi is 360. 2 pi is a full revolution. Pi is 180. That's where kids tend to go cross-eyed, is because the conversion is only half of a circle. So they think pi is a full circle because 1 to 1. 1 pi to 1 circle. No. 1 pi is 180.
So then would you put that? So 7 pi over 4 plus 8 pi over 4? No.
Yes. This is the part where you draw the angle. Draw the angle. Okay. If 180 is pi, your fractions are semicircles. So if I say something pi over 4, then break the top half into quarters, break the bottom half into quarters. Because now I can move 1, 2, 3, 4, 5, 6, 7 pi over 4, 7 quarters. There we go. No, I go negative direction.
Oh, and then
Uh-huh. The negative in this case only denotes direction, not which quadrant. And what really messes with you is then after that, what happens when it's more than a full revolution? What happens when I say negative 17 pi over 4? Where's that? Well, you don't simplify it. You have to show every rotation. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. pi over 4. Okay? So you would have to show that full set of revolutions. Now, it's coterminal with just negative pi over 4, but you got to show every bit of it. Oh, we're not blue anymore. There we go. Okay, so here we just got pi over 4, right? Add 8 pi over 4, 2 pi, versus negative angle. Ah, he's in my spot. Lap him. So we have to go negative 7 pi over 4 and then another revolution of negative 8 pi over 4 or negative 15 pi over 4. Okay. These look really fancy. A bunch of swirls and fractions and pi's all over the place. But it's just working in fractions. It's a bunch of pizzas. Okay. All right. Arc length. You got a little room in the middle of this to write because these do not take a lot of space. Take you down memory lane. Do you remember what the circumference of a circle is? 2 pi radius or pi diameter. Okay, pi times the diameter or 2 pi r. So that's the perimeter of a circle, but circles are special, so they get their own word, circumference. What if I only want part of it? What if I had an angle like 120 degrees and I didn't want the entire circumference? I wanted this, which is called an arc. An arc is often denoted with, I really hate that they do this, a little s. Right? That's why we always make sure that this part has a perpendicular when we do 5. They use little s for arc length, but in every geometry book that I was ever in, it was an L for arc length. Okay? So whatever we're going to use, my arc length, L, how am I going to find just that much of the circle? I can do this in degrees or radians, which is the new formula we're about to get.
You take the radian amount times the radius.
Well, yeah, that's the formula. How did you do this in geometry before you knew what a radian was? All right. You are going to get 13% of great-grandpa's inheritance. Here's $20,000. How much are you getting? Don't you take the portion, the percent, the fraction, the ratio, times the entire thing? Arc length was take the circumference and multiply it by, do I know what portion of the circle I have? How do I know it's 1/3? What about 120? That. It's how many degrees out of 360? That's how you did it back in geometry, or should have done it in geometry. Arc length is simply what portion of the circumference do you have? Well, it turns out when you take that degrees and convert it into 180 or pi over 180, cancel, 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 you end up with a much cleaner formula in radians that's just radians times radius. If you're in radians, this gets so much faster. I want you to have both of them written down because they're both legal. They're both going to do the same thing. But if I have the radians of my angle and the radius, I just multiply those and get 5 pi over 4. That's my arc length. Ta-da!
Do we have to like plug that in? Not plug it in, but like.
If you want a decimal equivalent with it, you can.
But do you want that?
I don't care. Now, again, if you're talking about the context of a real-world problem, you know, if I'm going to replace the tires on my truck, and I tell them that, well, I need a 5 pi over 4 radius on my rims, like, yeah. Okay, so I have two options. Option one, I can go old school and say 2 pi radius times degrees out of 360. And just clean it up. But option two says, well, that's just pi over 3 times 2. Done. If you know your degree to radian conversions. It's either that or you got to do this whole formula and you say, well, that's 1 over 6. That's 2, 3. So that's 2 times 1 times 1 times 1 is 2 pi over 1 by 1 by 1 by 3. Or you just know that 60 is pi over 3. Okay? So you get a choice of which method you want. I don't care, but you got to know both formulas. Go. Okay. If you are just not a fan of radians, A, next couple of weeks are going to suck. But B, you can just turn 135 into radians or use the degree formula. Just dump it in a degree formula. If you don't like 2 pi over 3 radians, then take 2 pi over 3 and convert it into degrees. Call it 120 degrees. And then use a degree formula. I don't care which you do. As long as you follow math law, there is more than one way to get to the answer. Okay? Oh, we're so close. And this is the one that kids have trouble with. No, we'll go through this and then we'll start with it again tomorrow because we're going to need to practice. Okay. Okay, we just kind of talked about this with the whole definition of radians. That I can use a radian is a radius. This much rotation equals this much length. I can use that to swap back and forth between what is called linear speed and rotational speed. If I know all the conversions, or maybe the people who made my vehicle know the conversions, I can find this many revolutions per minute will equate to this much distance traveled with my tire. That's how your speedometer works. Okay? So I can swap back and forth between them, but it means I have to cross that boundary. 1 radian, which is length, which is rotation, tired, is 1 radius, which is length. The two formulas I'm given, you probably remember this from way back when. You probably remember it more as velocity is distance over time. Except in this case, my distance specifically is going to be the arc length that has traveled. Because the distance is, think about a rolling tire. Have you ever like cut a tire or a circle or something and just laid it out as a big rectangle? Okay, that perimeter, that circumference is a linear distance that was traveled. That's why your speedometer is in miles per hour. I have literally rolled this many miles in that hour. Okay? If I want angular speed, you get this little W. W. It's like a W with them apple bottom jeans. Okay? It's got like, right? And it's rotation over time instead. This is where you would have revolutions per minute. Okay? I mean, come on, it's a Greek letter, but that looks like some badonkadonk right there. Okay? So, the only way that you are going to go from here, to go from linear to rotation or rotation to linear, distance versus radians. I have to cross this boundary. Now, we're going to go old school all the way back to physical science. And we're going to do unit analysis. Y'all remember those? Or dimensional analysis? Okay, here we go. During one delivery, the tires rotate at a rate of 140 revolutions per minute. I should write that. 140 revolutions to 1 minute. Okay. Find the angular speed in radians per minute instead. So this is the quick warm-up. To go from revolutions to radians, do I have a conversion factor that tells me this many revolutions is this many radians? Yes. What is 1 revolution in radians? 2 pi. So I have to multiply it by, which is it going to be? Is it going to be pi radians over revolution or revolution over pi radians? You want them to be kitty corners so they will cancel. So I'm going to say that 1 revolution, that's really bad writing, is 2 pi radians. And now, revolution cancels with revolution. You see the only units that you have left now are radians a minute, and that's what they wanted, radians per minute. So 140 by 2 pi is 280 pi. 1 by 1 is just 1, so radian per minute. But I said it so it counts, right? Damn. Just the collective shake of 20 heads going, no. There. Okay? 280 pi radians. Now, if I say 280 pi radians, well, that's the exact answer. That's the perfect answer. It's got pi in it. I could have a decimal approximation with it, and it would be, oh, about 900-ish. Okay. Down here. Come on. I want to go further. Okay. Write it down here. I'm just going to put it up here so it's easier to write. On one part of the trip on the next delivery, the tire turns at a constant rate of, I should write this, 2.5 revolutions per second. I need to turn that into miles per hour. Okay. This is how you can do things like convert the muzzle velocity on a paintball gun to how many miles per hour is that thing actually hitting my leg. Okay. I was really into that in high school. We would pressurize them like a bunch of farm kids who knew how to play with them. And then you'd have frozen ones, and yeah. We hurt people. We thought it was fun. We were stupid. 2.5 revolutions per second. If I want it in miles per hour, I can at least take care of that. How do I go from seconds to hours? What if I don't know that off the top of my head? Okay. So if you need to pit stop and say seconds to minutes and then minutes to hours, go for it. If you know that 3,600 seconds is 1 hour, then you're good to go. Okay, awesome. But what am I in right now? What are my units? I have revolutions per hour. I don't want revolutions per hour. I want miles per hour. This is rotation. Miles is linear. The only way that I'm going to get from rotation to linear is crossing the boundary of radians to radius. So can you get revolutions to radians first? Okay, so I'll multiply by 1 revolution is 2 pi radians. Okay, please tell me that your Algebra 1, your physical science teachers at least had you do this, the double slash, so you know which canceled out with which, so you can backtrack your work. Okay. I am now in radians. I know that 1 radian is 1 radius. Awesome. 1 radian is equal to 1 radius. Look at the picture. Do I know what 1 radius is? 15 inches. Since 1 radian is 1 radius, I can now swap my rotation into linear speed. I've crossed the boundary. Now I just need to switch it over to miles. Okay, first thing I need to do is go inches over to feet. 12 inches, 1 foot. And then, one of my favorite lines in any movie of all time, how many feet in a mile, Petey? 5,280. You're going to pick up this ball and run every one of them. Remember the Titans. Denzel Washington is an amazing actor. Okay. So there's inches, There's feet. And I now have multiply. Okay?